All right, let's jump right into this. The purpose of today's explainer is to unpack a really fascinating falsifiable hypothesis. We're looking at how a brand new foundation, specifically the Informational Physics Ontology, or IPO for short, was used to build the Unified Informational Math Framework. And credit where it's due, this whole framework comes from researcher, inventor, and author Kevin L. Brown. The big idea here? This UIM framework might just give us the toolkit to finally crack the top 10 unsolved problems in math. It's an entirely new way to look at why we get stuck. And spoiler alert, getting stuck might actually be the exact clue we need.
So we're going to treat this a bit like a detective story. On the agenda today, we'll start with those top 10 unsolved problems, then introduce Kevin Brown's UIM framework and this concept of structural pressure. After that, we'll test out the falsifiable hypothesis, run through the validation and falsification parameters, and wrap up with the real-world implications for AI. Let's get to it.
Section 1. The top 10 math problems. Puzzles that have resisted centuries of proof.
Okay, so these are the heavy hitters. You've probably heard of at least a couple of them. We've got the Riemann Hypothesis, which has literally been sitting wide open since 1859. There's P versus NP, basically the ultimate boss-level question in computer science. Then we've got Navier-Stokes in fluid flow, Young-Mills in quantum physics, and the Goldbach Conjecture, which asks surprisingly simple questions about whole numbers, but just refuses to be fully proven. These puzzles haven't survived just because people aren't trying hard enough. They survive because every single attempt eventually hits a massive, unbreakable wall.
To put that into perspective, just look at Navier-Stokes. At its core, it's just trying to map out how fluids flow, right? Like water moving through a pipe, or air rushing over an airplane wing. But finding a bulletproof mathematical rule to prove these equations will always work without them randomly breaking down or spitting out impossible infinite numbers is still a huge mystery. Our current math just kind of fails to keep it well behaved.
Moving on to Section 2, Kevin Brown's UIM framework, a new map for missing mathematics. Now, this brings us to a real game changer. As I mentioned earlier, this breakthrough comes from researcher, inventor, and author Kevin L. Brown. He developed the Informational Physics Ontology, the UIPO, and used it as the foundation for the Unified Informational Math Framework, or UIM. Brown didn't just build this to guess at the answers. He built it as a completely new way to map out exactly why these top 10 problems are stuck in the first place. So how does it work? Well, the UIM framework relies on a really elegant central rule with 3 basic steps: represent, preserve, and recover. Think of it like translating a famous novel into another language, and then translating it back into the original. If a crucial chapter goes missing during that translation, the whole story stops making sense, right? UIM forces us to ask, when we try to solve a complex math problem by changing its form, what exact piece of information gets lost? Pinpointing that missing piece shows us exactly where our mathematical map is broken. Section 3. What is structural pressure? When uncertainty concentrates. Okay, this is where things get really fascinating. We need to talk about structural proof pressure. See, instead of a math problem just getting messier and more confusing as thousands of people work on it, sometimes all those failed paths create a massive bottleneck. All the uncertainty concentrates around one tiny, specific missing link. It's like finding a single broken stepping stone in a massive river. That bottleneck creates structural pressure. We're not talking about physical pressure, obviously, but a highly measurable buildup of failed mathematical paths, all pointing at the exact same roadblock. And it's really interesting to see how this pressure actually builds up. Sometimes it's from what we call fatal node concentration, where dozens of different proof paths all rely on one single calculation, and if it's missing, the whole thing collapses. Or you see it when a bottleneck persists for decades, even as the math around it advances. There's also finite evidence saturation. That's when we have massive mounds of computer data pointing to an answer, but we still can't find the universal rule. And my personal favorite, when entirely independent research teams take completely different mathematical routes, but they all crash into the exact same missing bridge. That kind of convergence, that is a highly measurable, undeniable sign of structural pressure.
Which brings us to Section 4, the falsifiable hypothesis, predicting the breakthroughs.
So, what does this all mean? Well, using this pressure concept, the framework gives us a highly falsifiable hypothesis. It states that mathematical systems showing sustained, high structural proof pressure actually have a much higher probability of undergoing a major transition than low-pressure systems. Now, to be clear, it doesn't guarantee a problem will magically be solved tomorrow. It's all about probability. The hypothesis predicts that this massive bottleneck of pressure makes a huge sudden reorganization of the math significantly more likely to happen.
Section 5. Validation and falsification parameters. Testing the theory.
For this to be real, rigorous science, we have to know exactly how to test it. We validate the theory if a genuine transition happens, like if a missing bridge between math concepts is finally established in the pressure releases. But just as importantly, we need strict falsification parameters. We need to know exactly how this hypothesis could be proven wrong. For instance, if simple, ordinary things, like just looking at how old a problem is, can predict a breakthrough just as accurately as this pressure model, well, then the hypothesis fails. It also fails if we have to sneakily tweak the rules after a problem is solved to make it look like we predicted it. Testing this hypothesis against the top 10 unsolved problems is literally the perfect stress test, because they cover genuinely different, completely unrelated areas of mathematics.
And finally, Section 6. Real-world AI implications. Guiding the future of computing.
So why does this matter today? Well, when we use artificial intelligence to tackle math right now, we usually just ask it to search blindly through millions of possibilities. It's basically brute force. But with Kevin O'Brown's UIM framework, we can ask the AI highly targeted questions. We can ask which unresolved proposition currently carries the largest share of the remaining proof structure. Instead of guessing, we can literally tell the AI to go hunt down the specific pressure points. By mapping out this structural pressure, AI can prioritize exact bottlenecks. It's a total game changer for how we formulate research strategies. Instead of humans and computers just throwing darts in the dark, we can use mathematical knowledge graphs, which are essentially giant digital maps of everything we know, to highlight these exact pressure nodes. This guides researchers and AI proof assistants straight to the areas that offer the highest possible leverage for a massive breakthrough.
Ultimately, this whole explainer leaves us with a pretty profound thought. The organization of unresolved mathematics itself actually contains information about the likelihood of a structural reorganization. In other words, the roadblocks aren't just obstacles, they are the map. The very shape of what we don't know yet might just be the exact blueprint we need to find the answer. And if the shape of our ignorance can actually guide us to the truth, what other mysteries in the universe are just waiting for us to measure the pressure?